Welcome back, and let's move on to the final sections for this week. How do we quantify? So again, quantities using numbers now. How do we measure heat? How do we put a number to it? So you might think, well, we use a thermometer. Remember that that's a way to measure temperature. Heat, we're talking about the actual energy involved. So how do we measure the heat or the thermal energy involved? As I mentioned last time, we can only measure it when it's moving from one thing to another. You cannot just look at, an object and tell me how much energy is in there. Heat is the thermal energy that gets transferred. So, just like we had a special technique for acids and bases called titration, calorimetry, it doesn't need to have a capital C, but calorimetry is the study of how energy flows, and it's also a lab procedure that you can do to measure how much energy has been transferred from one thing to another. As a reminder, energy that we'll be talking about is measured in joules or calories. I'll be using those depending on the problem, but energy is measured in these units. So what is calorimetry? Again, it's a lab technique. And again, there was no transition on that slide, but it's a technique that measures how much heat is transferred. And this Q, it's just heat transfer. I don't recall why it's Q in particular, but it's Q. So, yes, this slide can definitely be overwhelming, but it's how much, so this is like 100 grams of water or something. It's how much heat did it gain or lose inside a reaction. And you find that by taking the mass, multiplying it by something we call the specific heat capacity, which I can talk about more in a second, and the change in temperature. So it's three quantities multiplied together. And maybe it makes a little bit of sense. It's like, how much did the temperature change? Like, let's say it changed 5 degrees Celsius. And if I had 1 gram of it, maybe you would expect these both to multiply to tell you how much heat change happened. Versus, if I had 105 degrees Celsius, then the amount of change, like if it rose 105 degrees, you would expect there to be a lot more heat transferred because it changed by much more temperature. Or if instead of a gram I had like 10 grams, if I have more stuff changing by this much temperature, the heat transfer also would have been bigger. So it relates to mass and temperature, and that makes sense. But what is this specific heat capacity thing? Where does that come into play? The specific heat capacity, and I'm sorry it's not on this slide, but the specific heat capacity is a constant that's measured for every substance, and it depends on the substance. You can think of it as how much heat can be stored, like what is the capacity of this specific substance to hold heat. You may have even heard the sentence before, water has a high specific heat capacity. And this is what we're talking about. It means that for every gram of water, changing 1 degree Celsius will affect the heat change by a lot. So again, right here, the specific heat of water is just this constant. It's, oh my gosh, sorry I crossed that out, but 4.18 joules per gram Celsius. And you're like, what kind of unit is joules per gram Celsius? Turns out it works out very nicely because mass times C times delta T, let's do some quick almost dimensional analysis here. If I use grams and then C is in joules per gram Celsius and T is in Celsius, then notice how the Celsiuses cancel and the grams cancel and you're left with joules, which is a unit of energy. Again, this is C, the specific heat capacity, is just some constant that we've measured that's specific to a substance. Water has a particularly high one. You might also notice that water has a specific heat capacity of 1 calorie per gram degree Celsius. We actually define what a calorie is based on this. So the based on the specific heat capacity of water. That's what it means. You may have heard the sentence also, a calorie is how much energy it would take to raise 1 gram of water 1 degree Celsius. Again, specific heat capacity, it's how much energy it takes to raise each gram of the substance up by 1 degree Celsius. And that actually is different from one thing to another. For metals, it's really easy. Metals heat up and cool down very quickly. Water heats up and cools down very slowly. So there are some 2 practice questions you can think about. I'll do the first one. Well, I would just plug it in. I'd plug in this for mass. 25 degrees Celsius is the change in temperature. And I have my specific heat right above. And then I can calculate the calories. So 10 times 1 calorie per gram Celsius times 25 should be 250 calories. Okay. So now that we have a formula, I guess we can see that to calculate how much energy has come into or gone out of the system, you'll have to assume that however much heat you lost is however much heat you gained. Again, the amount of heat that the system lost is how much the surroundings gained, to be very clear. So calorimetry usually have like a styrofoam cup, and that's your system, and then you put that into like a tub of water, which is the surroundings. And you just have a thermometer on the outside, and you can see that, let's say, the water changed some amount, like maybe 5 degrees Celsius increase. That means we're assuming all the heat that the water gained was lost by the cup. Of course, in actuality, labs can have errors, it won't be perfect, but that's what I mean by heat lost is heat gained. The heat lost by one thing is gained by the other. Again, it's a restatement of the first law of thermodynamics, though of course in reality there's some surroundings over here above your system that maybe weren't captured by your lab setup. Alright, so if equal masses of 2 substances are given the same amount of heat to absorb, and the temperature of B is suddenly a lot higher than the temperature of A, which one has the higher specific heat capacity? You can also look at this. Again, these are on the exit ticket. Feel free to pull that up and do them now. Oh, looks like this one was actually done for us on the slides. So it should actually end up right there. And you can do the math out. Post on Piazza, ask me if you didn't get that answer. Alright, again, these are not my slides, but it looks to me that this is basically the same thing. It's reminding you what specific heat capacity is. They solved for C, given this equation here. Or you can go either way, I guess. They're both true. Again, water has this constant that you'll see a few times. That's the specific heat capacity. That's just how it is. Alright, the rest of the slides seem to go on a bit about phase changes. So, again, in physical changes, changes of state, you gain or lose energy. This gets into a bit much, and I might recommend you look at the simulation, but there's a specific amount of heat needed to melt a substance, and fusion is actually the old term for melting. So this fancy term heat of fusion just means how much heat do you need to melt something. Again, that would be specific to a substance. The heat of fusion for water should be different from that of, let's say, aluminum. Again, the heat you need to vaporize something is called the heat of vaporization. There's actually a pretty interesting phase change graph that kind of shows what happens as I add energy to a system. So maybe this doesn't look that interesting to you because you're like, yeah, the solid over time as you add energy plus joules, it's getting hotter, and then it hits 0 degrees and Celsius, and you would expect it to start melting. That's the freezing point of water. But what's interesting there is actually, if you do this experiment, the temperature will stay at 0 for a while, even though you're adding heat. That's like very surprising, I would say. Like you're literally adding energy throughout this whole point, and it's not changing temperature. Weird. Then you keep adding energy, keep adding energy. It's, you know, higher temperature water, now it's like 60-degree water. And then eventually when you hit 100 degrees, again, when you hit 100 degrees, it'll start to boil, right? But turns out you can keep adding energy for a while. I'm not sure why this axis says time. I would really like it to say like adding energy or something. I'm adding more energy, and it's still at 100 degrees. What this practically means is if you're boiling water on the stove and you keep turning up the heat and it's already boiling, like you see the bubbles moving, you're not actually turning the water any hotter. The maximum temperature of water is 100 degrees for this whole time, which is, again, crazy. And then eventually, at some point, it becomes a gas, and it keeps heating up, and gases can get very, very hot until it becomes plasma, but we won't get there. An interesting question to consider, and it might be a little bit beyond the scope of this chemistry class, but is what's going on during these phase changes? Like, why is it staying the same temperature even though you're adding energy? Because normally when I add, here are some particles. If I'm adding heat to a system, like, what are you envisioning is happening there? And again, there's a simulation for this. If I'm adding heat, normally it means like the particles are moving faster. But something special happens at these places, and what this flat line means is literally the particles are not moving any faster as you add more temperature. Or heat, sorry. That heat is going to something else. It's doing something special. And hopefully you can look at the simulation and think about what exactly is happening. I'm going to actually stop talking about the slides here because I think the next part gets a bit too much into calculation. But if you have questions about it, feel free to ask me anyway. I'd be happy to answer it if you want to go a little bit ahead. Alright, so that is this week. Again, this week is a little bit more qualitative than quantitative. You should have everything you need to look at the week assessment check-in sort of thing. Again, we really do want this one to be a little bit more of a what do you understand right now? Please don't look up the answers to them. It's okay if it's not a textbook correct answer. We just want to see where you are at this point so we can better cater the future weeks to your understandings. All right, thanks so much for listening. I hope you have a great week, and see you possibly in person, I guess. Synchronously next week. Or later this week.